For over half a century, one simple rule has governed our technological world: Moore's Law, the idea that the number of transistors on a chip doubles roughly every 2 years, making our devices faster, smaller, and more powerful. But what happens when that law breaks down? What happens when the physical limits of silicon are reached? We're standing on the brink of that very moment, a computational cliff edge. And the answer to what lies beyond isn't just a better chip, it's a completely new kind of brain. This is the dawn of neuromorphic computing. Forget everything you know about traditional ones and zeros. We're talking about building computers that think like us, that learn like us, modeled directly on the human brain. Your brain operates on just 20 watts of power less than a dim light bulb, yet it can process complex information, recognize faces in a crowd, and create art. A supercomputer trying to do the same thing would need enough energy to power a small town. This incredible efficiency is what scientists are now capturing in silicon. So how do these brain-like chips work? Unlike a standard CPU that processes tasks one by one, a neuromorphic chip works in parallel, just like the neurons in your head. It uses spikes, which are tiny pulses of electrical energy, to communicate. This is called event-driven processing. The chip only uses power when a spike occurs, when there's new information to process. This is fundamentally different from your laptop, which is constantly burning energy whether you're editing a video or just staring at the screen. This spiking neural network design allows them to learn and adapt in real time without being connected to a massive data center. Major players are already making incredible strides. Take Intel's Lloyd chip. It packs over 1 million digital neurons onto a tiny piece of silicon. It's learned to smell hazardous chemicals better than a trained dog, a feat that would be incredibly difficult for traditional AI. IBM's TrueNorth chip is another titan in this space, designed for ultra-low power sensing and pattern recognition. These aren't just lab experiments anymore. They're being tested in drones that can navigate without GPS, in medical devices that can detect early signs of disease from subtle bodily cues, and in smart factories that can predict equipment failure before it happens. The implications are staggering. Think about AI. Today's AI models, like the ones that power chatbots or generate images, require colossal amounts of data and energy to train. A single AI training run can have the carbon footprint of hundreds of transatlantic flights. Neuromorphic AI could learn on the fly, using a fraction of the energy. Imagine your smartphone having a truly intelligent assistant that learns your habits and anticipates your needs without ever sending your data to the cloud. Imagine robots that can adapt to new environments instantly, or self-driving cars that can react to unforeseen obstacles with human-like intuition. This isn't just an upgrade, it's a paradigm shift. By 2035, some analysts predict that neuromorphic computing could account for over 20% of the global computing market. That's a multi-trillion-dollar revolution waiting to happen. It will unlock computing power that we can currently only dream of, solving problems in climate science, drug discovery, and materials engineering that are impossible today. We're not just moving beyond Moore's Law. We're stepping into an entirely new era of intelligence. An era where our technology isn't just programmed, it's inspired by the 3 pounds of matter sitting inside our own skulls. This leap forward promises a future of unimaginable efficiency and intelligence, creating a world that is smarter, more responsive, and more connected than ever before. But as we build machines that think more and more like us, we have to ask a critical question. If we create a computer that can learn, adapt, and process information just like a human brain, at what point does it stop being just a machine? Thanks for watching, and don't forget to subscribe for more deep dives into our technological future.